we're going to talk about two things. The first being thermal expansion and the second being stress concentration. So with thermal expansion, it's really pretty straightforward. The temperature, when the temperature increases, essentially we have expansion that occurs, right? So if I heat a column or a bar or a rod or whatever, if I heat it up, it's going to lengthen. If I cool it down, it's going to shrink. And it does this linearly, okay? And it does it using the coefficient of thermal expansion, which is a variable that's found experimentally, okay? And that displacement is just that coefficient, right? So the increase in length or decrease in length is that coefficient times the change in temperature times the original length of the bar. Again, this alpha is found experimentally. You can look it up in the back of the book in the tables. Once you know that and you know the change in temperature and the original length, I can find the deformation, the elongation of that rod. So really that's pretty straightforward to figure that out. The other thing we want to talk about is stress concentrations. And there's a couple of different ways that we look at it. I'm just going to look here at kind of a reduction in the cross-sectional area, okay, where I've got a fillet basically. Okay, so if I have a stress on this thing, okay, if I look at the stress distribution at that change in cross-sectional area, okay, I've got an increase in my stress. Okay, so something similar could be like if you've got a crack in the system, okay, it's going to be much easier for you to continue to break it with that crack. Other ones, maybe you've seen, if you're trying to open a bag of something from the, some sort of food item, okay, they'll put a little notch in it. That way it makes it easier for you because of this increased stress. You don't have to put as much force to get that thing to tear open, okay? So that's essentially what's happening there, okay? We have very complex stress distributions at that change in cross-section. Again, I'm just looking at this little elbow here. There's other ones that you can look at in the book, and if you check out the example that I do, I show a couple of different ones, okay? Now, fortunately for us, we don't need to know that whole stress distribution. We just care what the maximum is, because the maximum is when the thing fails, and that's what we want to generally avoid as an engineer. We want to design it so it does not fail. So we're just looking for that maximum stress, okay? So we have this thing called a stress concentration factor. And again, this is also found experimentally, just like alpha was, okay? And we have a chart over here to help us find K, okay? And that K is essentially the maximum stress, which is what we're interested in finding and what we want to keep below, divided by the average stress, okay? So let me go over to the plot here and show you what we're looking at. So again, we're looking for K here. And you notice we got several different lines here, and these are the width over the height, which is the big area divided by the little area's height, okay? That ratio, okay? And as you can see, generally, the higher that gets, the bigger difference between the two areas, okay, the bigger K gets. And that means the larger the maximum stress is as compared to the average stress. The average stress is the stress at the smallest area, so just always remember that. So that average stress is the force over the small height times the thickness, okay? And then RH is also here. R is the radius of the fillet, and then H is the height of that. So again, the smaller R gets, okay, as I move this way, my K goes up, okay, which I think makes sense. If you've got a really sharp corner, i.e. very, very small, it's going to be a lot easier to break that than if I have a nice rounded corner, okay? So you just follow, you just find WH and RH, figure out, which line to look at, which R to look at, and then just come over and you find your K. And then you plug that into this, and basically you find how much that average normal stress increases due to that stress concentration that's occurring at that change in area. Okay, so in order to solve those problems, you'll need this chart. Again, this chart is found experimentally. And if you check out the example, I show you exactly how to deal with that.